So in this first recap of this last week's lectures, I'm going to talk about using epsilon 2 techniques in proofs and how to do it. I'm going to create another short lecture that involves bounding sequences and where that's used. And then that will define the two videos will define together the recap for the big topics of the Wednesday's lecture, since we didn't have a lecture on Labor Day. So we started with an epsilon over 2 argument to prove that limits are unique. The basic question was, if I know that a sequence converges to a limit, how do I know it's the limit? So there's all this discussion I put in here from previous times I've typed up lecture notes, and I really encourage you to read it. One of the things I get to is the type of question that leads to a claim that which if proven becomes a theorem, and the question kind of motivates the idea of an epsilon over 2 argument, because you basically say, well, if S sub n converges to S, how do I know it doesn't also converge to T? So then you have two things, right? You have an S and a T, and they're both related to a sequence. So the same sequence in this case, but you're basically saying, well, I have two types of convergences I might have to deal with. And as soon as there's two, you kind of know you're going to have to do an epsilon over 2 if you're going to show that things are the same, or have some sort of property involving the difference being made less than an epsilon, which is what I highlighted here. And so we talked, first 5-10 minutes of class just motivating that basic structure, and then the whole point is you know the object you're trying to make less than an epsilon, and then what you typically have to do is think of some creative way of shoehorning in the things that these other terms are related to, because the point of the argument that you're making is, I don't really know why S minus T should be less than some epsilon. It should be less than any epsilon greater than 0 at all. What I do know is that Sn minus S in absolute value and Sn minus T in absolute value should be as small as I need to. And maybe in this case, if I make each one less than an epsilon over 2 separately, then when I add them together, the sum is less than epsilon. You say, oh, that's how I can show S minus T in absolute value is less than epsilon, because I just don't know how to do it directly, right? S and T are the result of taking the limit of a sequence. So what I need to do is get the terms of the sequence into this relationship somehow, because those are the terms that I know how to compare to S and compare to T. So as soon as you have that mindset, it almost hopefully becomes obvious if you spend some time with it, or at least it doesn't seem mysterious at the very least that you should be doing like an epsilon over 2 argument. Of course, one of the things that you have, and I talk about this in here as well, is if I'm saying that S sub n converges to S and S sub n converges to T, and I'm in this world where I don't know that S and T are different, I don't know that it's converging to each of these limits at the same rate. And so, that for a given epsilon over 2, if epsilon is greater than 0, epsilon over 2 is greater than 0. And for that error tolerance, the distance I have, or the number of terms I have to go out in the sequence Sn might have to be greater than some n1 in order to make that difference Sn minus S less than epsilon over 2. While for the same sequence, but its difference to T, I might have to go out into terms in order to make it less than epsilon over 2. And these can all be, by the way, these inequalities can all be, they don't have to be strict. There's no reason for them to be strict. This is just based on the old notes. And so we did this here, just formalizing. We went through this in class. So I'll just let this stay on the screen for a second if you want to pause it and compare to what you wrote down. But you basically see that we're using the convergence of the sequences. And I have a typo here, so I'm going to fix that in my notes. That is Sn. These are my master notes, and they have a typo. And that's Sn. There you go. So the sequence Sn converges to S, the sequence Sn converges to T. That means that I can choose an n1 and I can choose an n2 such that n greater than or equal to n1 gives me the epsilon over 2 bound for Sn minus S in absolute value, and n greater than or equal to n2 gives me the bound of epsilon over 2 for the absolute value of Sn minus T. So there you go. And then you just say, look, I need both of these things to be true simultaneously. So I choose n to be the max of them. And this is just written up a little differently than I did in class. You let n be something greater than or equal to n. You kind of want to fix it. You can choose one to be fixed. But then once you have that, you then get the inequality you want. So, all right, it's a version of what we did in class. Okay, so I'm gonna skip the boundedness discussion here. I'm just going to assume that we have bounded. And then we went to this theorem, which was 9.4, and it said if Sn converges to S and Tn converges to T, then the sequence defined by the term-by-term product has a limit that is the product of the limits, and the limit of the product is the product of the limits, right? That's this theorem. So again, like, just you should have alarm bells going off in your head that this has to be an epsilon over 2 argument, because I'm dealing with two sequences that converge. And then I'm doing something involving both sequences, which means somehow I'm going to use that Sn converges to S and Tn converges to T. And I'm going to have to use that difference can be made small somehow. And you say, okay, that's more than likely going to involve an epsilon over 2 argument, so that I can kind of balance the errors, balance the epsilons, to be epsilon over 2 in each term, so that the sum is epsilon. So we went through the idea of the scratch work for this, and then there's just this technical part where we ended up saying, if I have a convergent sequence, then it's bounded, so that we could fix the bound for one of them. But the basic idea beside that mechanism, I don't want to get into the details of that. We went through it in class, but you basically have these two terms separately. I'm just going to highlight them here on the screen, circle them here and here. And the objective is I want to make each of these less than epsilon over 2. And so if you start with, like, I'll do this. If I say I want to make the absolute value of S times the absolute value of Tn minus T less than epsilon over 2, then you want to say, well, I'd like to make Tn minus T less than epsilon over 2 times the absolute value of S. Doing that is assuming that you can divide by absolute value of S. I don't know that it's non-zero. So one thing you can do is you can say, well, I'm going to make this I'm going to take absolute value of S and add 1 to it. And if I take epsilon over 2 times that in the denominator, this term, then I know I'm not dividing by 0. And if I multiply by the absolute value of S on this side, for instance, then this would still be less than epsilon over 2. So it's just this technical detail, and I really try to emphasize that. You don't want to divide by 0. And we basically did the same thing for this other term as well. When we replaced the Tn by M, we don't know that this bound might be 0, and so we did the same thing. The whole point was we wanted to make this entire term, well, we take this one and we bound it to get rid of the dependence on n of the coefficient, and then we say I really want to make this less than epsilon over 2, and for the same reasons I just showed, you say, well, I don't know that I'm not dividing by 0, so I make sure I'm not dividing by 0 by taking n plus 1. But again, it's just epsilon over 2. It's just, it looks slightly more complicated, but if you think of it grouping the terms in this kind of gross way, this like the combination of the product, then you see epsilon over 2 is all over the place. So then I gave 9.2 as an activity for you to do. This is just a single sequence converging. Hopefully you got something like this. I'll just leave this on the screen for a second. If you want to pause it, compare to the work that I asked you to do, or maybe skip over this part, don't look at it if you haven't done the problem yet, and then you can compare to what I'm showing here on the screen. But I just want to emphasize, we're proving that sequences converge, so we still follow this very familiar 4-step pattern to the proofs. And so it's just like with this other argument, I kind of rearranged it from a little bit from what I did in class, but we still have these 4, you can still clearly identify the 4 steps in the proof. And then 9.3, I also asked you to do, this is the limit of the sum is the sum of the limits. And it's a very simple epsilon over 2 argument. And again, I'm just highlighting on the screen these very clear identification of the 4 steps. And I'm not doing the scratch work for this. I think it's more straightforward than the product one. So that's it. I just wanted to emphasize, again, you have 2 sequences here as well, and it's clearly then going to be an epsilon over 2 argument. So I'm going to end this recorded lecture, or this recorded summary here, and then I'm going to create a new recorded lecture that summarizes the use of bounds of a convergent sequence. So, okay.